Welcome to class, everyone. Let's just dive right into this explainer. Today, I'm putting on my math professor hat, and together we are going to completely demystify the mathematical number system. You know, if you've ever felt like numbers are just this random jumble of rules, get ready for a total paradigm shift. We're going to look at the whole system through the lens of a really fascinating family tree analogy. By understanding this hierarchy, I promise you, everything else is going to fall perfectly into place. Here is our syllabus for today's masterclass. We're going to quickly hit the welcome to the number system, map out the real versus the imaginary, dig into rational and irrational numbers, break down terminating and repeating decimals, look at integers, whole and natural numbers, and finally, wrap up with prime and composite numbers. Section 1. Welcome to the number system, the top of the family tree. All right, so we're starting at the absolute macro level here, looking at the ultimate parent of all numbers. Imagine complex numbers as the father of this massive hierarchy. This parent oversees absolutely everything. From this father figure, the entire mathematical world is born. But this parent has two very distinct children that make up both the reality and the non-reality of math. Moving on to Section 2, the real versus imaginary, the two children. Let's actually meet those two kids. The first child is the real numbers, which are exactly what they sound like, right? They're numbers we can physically plot on a number line. The second child is the imaginary numbers, which are a bit more rebellious. They involve negative values trapped inside square roots. Now, we aren't testing you on the imaginary child today, but just to make sure we're all on the same page, I want to use the Socratic method and ask you directly, if we're looking at -5, which kid does it belong to? If you said real, you hit the nail on the head. The crucial point here is that -5 is entirely real. Even though it's a negative, it still has an actual physical location on our number line. Imaginary numbers, on the other hand, are strictly confined to those bizarre negative values trapped inside square roots, and honestly, we're just leaving them alone today. Section 3, rational and irrational numbers, the core focus. Now, this is where it gets really interesting. We're looking at the real number's own children, and this brilliantly illustrates the core difference between them. Rational numbers, they play nicely. You can always write them as a neat, clean fraction, p over q, as long as the bottom number isn't 0. Think of super clear examples like 5/3 or even 22/7. Irrational numbers, though? Man, they are messy. They are these unsolvable root formats like the square root of 2 or the square root of 3. You absolutely cannot capture them in a simple fraction. They just won't fit. Section 4. Decimals, terminating and repeating. The ultimate rule of thumb. Okay, so here is the absolute ultimate rule of thumb. If a decimal calmly terminates like, 1 divided by 2 giving you exactly 0.5, it firmly belongs in the rational family. Easy, right? But even if it doesn't end, if it neatly repeats itself, like 1 divided by 3 giving you that looping 0.333 forever, it is still rational. And here's a fun pro tip for you. Denominators with 2 and 5, they create those nice terminating decimals. Multiples of 3, on the other hand, create the repeating loops. But conversely, what happens when a decimal goes on forever without any repeating pattern whatsoever? I mean, it's just pure chaos. That non-terminating, non-repeating decimal is perfectly defined as an irrational number. They literally cannot be tamed into a fraction, which is exactly why they get slapped with the irrational label. Section 5. Integers, whole and natural. Descending the rational branch. Descending further down this branch, we find categories of numbers you use every single day. Let's start with natural numbers. Just think of these as your basic counting numbers, 1, 2, 3, and so on. But pay attention here, because 0 makes all the difference. If you just add a 0 to the start of your natural numbers, boom, they instantly become whole numbers. It's a tiny little shift, but mathematically, it is a vital distinction. And what happens when we invite the negatives to the party? Well, we get integers. Integers are basically the complete package of the rational branch's non-fractions. They encompass all the positives, all the negatives, and 0, with absolutely no decimals or fractions allowed. None. If you're counting backward past 0, you're firmly in integer territory. Section 6. Prime and composite numbers, the micro level. Finally, let's examine things at the micro level by looking back at our natural numbers. They split into some very unique characters. So a prime number has exactly 2 factors, 1 and itself. A composite number has 3 or more. Simple enough, right? But listen, it is absolutely critical to remember that the number 1 sits totally alone as neither prime nor composite. Why? Because it only has one factor. Also, 2 is our only even prime number in the whole shebang. And hey, if you thought multiplying 2 primes always gives you an odd number, scratch that. Think again. 2 times 3 equals 6, which is totally even. Now, if we map this out, we can see exactly how these primes are distributed across the first 100 numbers. Between 1 and 50, there are exactly 15 prime numbers, and from 50 to 100, there are exactly 10. So, if you're prepping for an exam, or honestly just want to impress your friends at trivia, memorize this exact quantity. There are exactly 25 prime numbers between 1 and 100. It's just 15 plus 10. It's a really great little statistical anchor for the number line that is totally worth keeping in your back pocket. But what if you're faced with a massive number, like 1001, and you desperately need to know if it's prime? You definitely don't want to test every single number. No way. Just use this 3-step method to systematically hunt down its factors and prove it isn't prime. First, find a perfect square close to your number, like 1024, which is 32 squared. Second, list all the prime numbers smaller than that root, so, everything up to 31. Third, just divide your large number by those specific primes to see if it cuts evenly. If it does, like 1001 dividing evenly by 7, you've proved it isn't prime. It's basically a math superpower. All right, class is dismissed. But before you go, I want to leave you with this final, kind of mind-bending question about the infinite nature of the math we just explored. We've traced the tree from complex numbers all the way down to primes, but with the number system stretching to literally infinity, how far down the branches can you push these absolute rules before the patterns break? Just a little something to chew on. Thanks so much for joining this explainer, and keep learning.